Section 4.1, Exponential Functions. So let's let b denote a positive number. And so if b is a positive real number, then a function, f of x being equal to a real number, a positive real number b raised to some x value, is called an exponential function with base b. Now specifically that's because the variable x is the exponent on any positive real number b. Now, once we have these exponential functions, recall that we have a handful of exponent rules that will dictate how we can work with these functions. And so remember, we have a product rule, that is if I have a raised to some variable times a raised to a different variable, then because the bases are the same, that's the same thing as the matching base a raised to the x plus y power. Then also recall that if I have a raised to a negative power, that's the same thing as 1 divided by a raised to the positive power. Remember, similarly, you can also say that if you have 1 over a to the negative x, that's the same thing as a to the positive x. We also have a quotient rule, that is if you have matching bases being divided, then that's going to be the difference of the powers, so a of the top power minus the bottom power. We also have a power to a power rule, that is if you have a raised to the x power all raised to the y power, that's a product of the powers, so that's a to the xy. And if you have a product to a power, well, that's the same thing as saying if you have two numbers being multiplied together raised to a power, well, that's the same thing as a raised to the x power times b raised to the x power. It works the exact same way with quotients. That is, if you have a divided by b raised to the power x, that's the same thing as a to the x divided by b to the x. And so these are the power rules that we're going to use to work with these exponential functions. So what we're going to do now is we're going to use these powers and factorization of some form or fashion to rewrite each one of these expressions as either 2 raised to something times an x or 3 raised to a number times x. And so here I have 2 to the x over 6 to the x. Well, currently none of my power rules are going to work as they are, so what we need to do is we need to do a prime factorization of 6 to the x. We need to do a prime factorization of 6, where 6 is really the same thing as 2 times 3. And then I can rewrite this as 2 raised to the x power divided by 2 times 3 raised to the x power. But recognize that via our power rules, that is the same thing as 2 to the x over 2 to the x times 3 to the x. Then we have a couple things we can do. If we're trying to get these in a single 2 raised to a power, 3 raised to a power situation, I can go ahead and combine the 2 to the x divided by 2 to the x via the quotient rule, which is 2 to the x minus x times, well then if I have 3 to the x in the denominator, what's that's going to be? That's going to be 3 raised to the negative x power. And then x minus x is actually going to be 0, and so that's 2 to the 0 power times 3 to the negative x. And so this is one way we can do this, where the k on the 2 is 0, and the k on the 3 is negative 1. Also recognize that 2 raised to the 0 power is really 1. Anything raised to the 0 power is equal to 1, pending whether a is 0 or not. But if we ignore a being 0, then this still works out. And so this is the exact same thing as 3 to the negative x, and so there's that. Let's try it again. If I have 3 raised to the negative 5x divided by 3 to the negative 2x, well, because this is a quotient with matching bases, that's the same thing as 3 to the negative 5x minus negative 2x. Well, that's then going to be 3 to the negative 5 minus 2, that's negative 5 plus 2x. And so, because those things are like terms, that is negative 3x. And so we're done. Here we have 16 to the x divided by 8 to the negative x. Once again, I need to have matching bases, so there's nothing I can do at this moment. But if we consider that 16 via factor tree is really 2 times 8, which is 2 times 4, which is 2 times 2, I see that 16 is 2 to the 4th, and 8 is actually 2 cubed, and so 8 is equal to 2 cubed. And so I can rewrite this as 2 to the 4th raised to the x power divided by 2 cubed raised to the negative x power. Well, that's the same thing as 2 to the 4x divided by 2 to the negative 3x. Then the quotient rule for powers is going to say that this is the same thing as 2 to the 4x minus 3x, which is the exact same thing as 2 to the 7x. And so there we are. Well, then if we have exponentials, let's combine all of this on the left-hand side as much as we can, and then if possible we're going to rewrite 27 using a matching base, and I'll show you what I mean. So first off, if I have 3 to the 2x times 3 squared all to the 4th power, order of operations, I can work with this parentheses first, so that's really going to be the same thing as 3 to the 2x plus 2, right? Because multiplication is addition, and then all raised to the 4th power. Okay, so then this is all equal to 27. That's still true. Well, then powers to a power, that's going to be the same thing as 3 raised to, and I'm going to go ahead and distribute the 4 over the binomial. This is then going to be 4 times 2 is 8x plus 8 is equal to 27. At this point, I have a single base raised to a power. And so my real question now is 27, are we able to write 27 as 3 raised to a power? And so if I were to try to find a prime factor tree, 27 divided by 3 is going to be 9, 9 divided by 3 is going to be 3, and so 27 is the same thing as 3 cubed. And so that means that all of this tells me that 3 raised to the 8x plus 8 is the same thing as, well, 27 is really 3 cubed. Well, at this point, because we have matching bases, you can just set the powers equal to each other. Because if this is an equation, I now know that 3 must equal 8x plus 8. So, 8x plus 8 has to equal 3, do basic algebra, minus 8 minus 8. That says that 8x is equal to negative 5. Divide by 8. Divide by 8. I then get that x is equal to negative 5/8. And so I claim that this equation here has a solution of x equals negative 5/8. And so in general, if you have an exponential function or an exponential equation and you're trying to solve it, try to get it to a single base, usually prime number is hopefully what you're looking for, a single prime number raised to some power, or a product of primes raised to powers. And if you do that, then you can work on the other side and try to get it in terms of a set of prime numbers raised to a power. Well, now that we've spoken about exponential functions in general, we're going to talk about a specific exponential function, that is the exponential function of e raised to the x power. Now, when considering e, the book gives a definition, and that is there's this particular number e, which has a slope exactly 1 at x equals 0. That's true. But a little more background history. Mathematicians were interested in a couple things. Some of them were actually just calculating compounding interest, and they discovered this number e. And then some other mathematicians were curious, and they wanted to know what function has a derivative that is itself. That is, what function has a rate of change that is its own function. And they discovered this number e, which is approximately 2.7. E is just a number, okay? Just want to reiterate, it's a number. And for the sake of it, you can say it's about 2.7. Your calculator has an e button, so if you need actual calculations, check that out. Now, when considering the exponential function y equals e to the kx, it's perfectly reasonable for us to sketch the graph if we so desire. And so, for the sake of things, let's make this the x-axis, this is the y-axis, and then we can actually talk about its properties. And so, properties of the exponential function e to the kx. Now, if you change k, a little bit of this stuff changes, but it's still going to be true that 0, 1 is on the graph. With some tick marks, let's just make each single tick mark worth 1. And then if that's the case, at the value 0, 1 is going to be on the graph. And this is going to be true for any e raised to the kx power. Okay? Now, if we start doing any type of weird transformations, that may change, but that's okay. Okay. Well, then, a couple things. The deal is that the graph is going to lie strictly above the x-axis. That is, e to the kx is never going to be 0. Now, if k is positive, the graph is going to be increasing and concave up, and so it will specifically look something like this. Now, it's going to grow pretty quickly. But once again, if k is positive, it looks like this. Now, x, the x-axis, is actually going to be a horizontal asymptote. Okay? Now, on the other hand, if k is negative, then the only thing that really changes is that we get a decreasing function, and as we keep moving further and further right, we're going to approach the x-axis, and so it's specifically going to look like this. Okay? But in general, if k is positive, we get this function, which is concave up, and it's increasing as we move left to right. And this is just a quick sketch. Now, once again, the interesting thing about e, and some mathematicians discovered the value e specifically because they were asking the question, what function that when you take the derivative of itself gives you itself, okay? And so the answer to this question is specifically that the derivative, d dx, of the function e to the x is equal to e to the x. Now, this can be a little bit tricky because we might have some chain rule involved, but if we have chain rule, that's okay. But what matters is that the derivative of the e function, where it's just e to the x power, is e to the x power. So now let's actually solve this equation here. So I've got e to the 1 minus x is equal to e squared. Well, notice that we have matching bases e. E is just a number. Since it's just a number, I know that I can set the exponents equal. 1 minus x then must equal 2. 1 minus x equals 2. Minus 1, negative x is equal to positive 1. Divide by negative 1, divide by negative 1. I get that x is equal to negative 1. So for this equation, we found that solution. And then I have a function that I'm trying to take the derivative of. And so if this is y is equal to x squared plus x plus 1, all times e to the x, if you wanted, you could distribute e to the x, but I think that might be a little more complicated because then you have lots of tiny product rules occurring. Whereas here, we just have one product rule, where I can think about this as f of x times g of x. And so just to keep us on track, remember that our product rule, being y prime, is then going to equal g times f prime plus f times g prime. And since that's the case, if we want, we can go ahead and find f prime. F prime of x is going to be 2x to the first plus 1 plus 0. G prime of x, well, g of x is e to the x. The derivative of the function e to the x is e to the x. So then when I find the derivative of y prime, that's going to give me g, that's e to the x, times f prime. Well, f prime is 2x plus 1 plus, product rule, f times g prime. So f, that's going to be x squared plus x plus 1, and then times g prime, but the derivative of e to the x is e to the x. Now at this point, we could distribute those e to the x's, and we could clean this up a little bit. And for the sake of practice, why not? Or I could actually factor out the e to the x from both of those. Then I get e to the x times 2x plus 1 plus x squared plus x plus 1. But that's just going to be e to the x times x squared plus 3x plus 2. Not that this step was necessary, but once again, if you want, you could distribute e to the x. Either way, I claim this is our derivative.